Hello students, this video is in continuation with our previous video on graph coloring. In this video we'll discuss some graph coloring theorem. So the first theorem is prove that following statements are equivalent for a graph G. G is two colorable, G is bipartite, G contains no odd cycle. So to prove this, we'll first prove A implies B, then we'll prove B implies C, and then we'll prove C implies A. So let's start with A implies B. A implies B says that if G is two colorable, then G is bipartite. So let G be a two colorable graph, then we have to show that G is bipartite. So as G is two colorable, so let vertices of G are either colored with red or blue color, or two color will have only two color on the vertices. So let those two colors be red or blue. So I have made the vertices like this. Here I have put the red vertices of that graph, and here I have put the blue vertices of the graph. And then let V1 be the set of all red color vertices. So these vertices make up the set V1 and these vertices make up the set V2. Now as it's a two colorable, so all the red color vertices will not be adjacent to each other, right? This cannot be joined with this cannot be joined with this vertex, right? And red color vertex can be joined with blue color vertices. These can be joined, right? Any red color can be joined to any blue color vertex. Any blue color vertex can be joined to a red color vertex. So graph will be something like this. Okay, it can be like this also. It can be like this also. It will be it will be something of this kind, where red vertices will be connected to blue vertices, right? So here these vertices are connected to other set of vertices. So such kind of graph are called bipartite graphs only, right? You can see that where one kind of vertices, one side of vertices connected to another side of vertices. These kind of graphs have bipartite graphs only. So here we prove that G is a bipartite graph. Next we have to prove B implies C. B says that if G is bipartite, then we have to prove that G contains no odd cycle. So B implies C. If G is a bipartite, then we have to show that G contains no odd cycle. So what we do, we divide our vertices of bipartite graph into V1 and V2. So V1, V2 is a partition of vertices of G of the bipartite graph. Okay. Now let's take some x in this set V1. Let's take a vertex x in this set V1. So we'll start a cycle from x. Obviously, if something is here, then it will go to the other side. It will go to V2. Okay. So any cycle beginning from x will go to a vertex which is in V2. So let it be joined to vertex y belonging to V2. Okay, so this x will go to y only, and then to a vertex in V1, and then it again will go to some vertex in V1, and this will continue, right? Cycle will go like this, from vertex of V1 to vertex of V2, and then to vertex of V1, then again to a vertex of V2. If there is an edge here, then only. Okay, so this will continue. And you know, in a cycle, initial vertex is always same as the final vertex. So if cycle begins here, it goes to vertex of V2, then again it come back to the vertex of V1, then it has to go back to X. But as you know, there can't be an edge here, because in bipartite graph there can't be an edge between two vertices of the same subset. V1 is a subset, these vertices are from V1, so there can't be edge here. Okay, so to go back to X, it will again trace the same path. So it came like this, and then again it will trace the same path, and you can see then it means whatever the length of this whatever the length of this path is, it will again repeat that, so it will become 2 times. So it will be even, it can't be odd. So when cycle get complete, it return to x. Okay, so it is even, so it will have even length, and if it's even, there will be no odd cycle. So this proves B implies C. Next, C implies A. So what does C says? C says G contains no odd cycle, and we have to prove that G is 2 colorable. Okay, so let G dash be a cycle in G of even length. If we have no odd cycle in G, we can assume that G dash is a cycle in G of even length. Like this is a cycle. It starts from here, it has even length 1, 2, 3, 4, 5, 6. So it has an even length. Okay, so we have to prove that G is 2 colorable. We'll prove that this is 2 colorable. Let some vertex be colored red. Okay, we'll color one of the vertex of this graph G dash as red. So let this be red. Okay, then the adjacent vertex will be colored green, right? The next vertex to this will be colored green. We can't give the same color to this vertex. So let this vertex is colored green. Okay, we are taking this vertex. So let this vertex is colored green. Then again next vertex can be given green color, so it will be given red color. Okay, and this continues, then red, then green, then again red, and then green. So in this way the whole graph will be colored, and it will look like this. So only 2 colors are used here in this graph, so hence it is 2 colorable. So this proves that it is 2 colorable graph. So in this way we have proved A implies B, B implies C, and C implies A. So these 3 statements are equivalent to each other. Next, we have a very important theorem, which is 5 color theorem. It says that if G is planar, then chromatic number of G is less than or equal to 5. If we have a planar graph, then that planar graph can be colored with 5 colors or less than 5 colors. Okay. So to prove this theorem, we'll do a lemma first. The lemma is, in a planar graph where G is equal to V, E, we have at least one vertex whose degree is less than or equal to 5. So let's prove this lemma. Let degree of each vertex of G be greater than 6. So we'll prove this lemma using contradiction. So we assume that all the vertex of G have degree greater than 6. So if there are V vertices, so each vertex will have a degree greater than 6. So sum of the degrees will be greater than or equal to 6 times V. Okay, so sum of the degree of the vertices of G will be greater than or equal to 6V. So sum of the degree of the vertices will be greater than or equal to 6. All right. So and by first theorem of graph theory, we have sum of degree of all the vertices is equal to 2 times the number of edges. So these two things gives us that 6V is less than or equal to 2E. If you'll put degree of sum of degree of all the vertices equal to 2E here, you get 6V less than equal to 2E. So it gives us V is less than equal to 2 by 6, which is 1 by 3E. Next, we'll use this result which we have proved in the video on planar graphs. We have proved this result. We have proved this inequality in the video in which I have discussed about bipartite and planar graphs. You can watch that video to see the proof of this result. We'll use this inequality that if G is a simple connected planar graph with more than one edge, then the following inequality holds. And the inequality is, this inequality will be using this inequality: 2 is greater than or equal to 3 times the number of faces or regions. So we'll be using it here. So by previous result, 2E is greater than or equal to 3R, which gives me R is less than or equal to 2 by 3E. Now adding 1 and 2, when we'll add 1 and 2, we'll get v plus r less than equal to 1 by 3e plus 2 by 3e. Okay, 1 by 3e plus 2 by 3e becomes e. So v plus r is less than or equal to e. Name this as equation 3. Then by our Euler's formula, we have v plus r is equal to e plus 2. So this is the value of v plus r less than equal to e. This is value of v plus r equal to e plus 2. So using 3 and 4, we get, if we put v plus r equal to e plus 2 here, we get e plus 2 less than or equal to e. So subtracting this e from this e, I get 2 less than equal to 0, which is not possible. 2 can't be less than 0, right? So our supposition, we supposed in the starting that each vertex of G has degree greater than or equal to 6. So our supposition is wrong. So there exists a vertex in G which has degree less than or equal to 5. So our supposition is wrong. There exists a vertex in planar graph whose degree is less than or equal to 5. So we'll be using this lemma in our theorem. Okay, so our theorem is 5 color theorem. If G is planar, then chromatic number of G is less than or equal to 5. Any planar graph can be colored with 5 or less than 5 colors. So we'll prove this theorem using induction on the number of vertices. So if there is only one vertex, then only one color is required to color G. If there is one vertex only, you can put one color on that vertex. So chromatic number will be 1, which is less than 5. So the theorem is true for the graph in which there is only one vertex. Now let us suppose that all planar graph with n vertices have chromatic number less than or equal to 5. So this is our induction supposition that any planar graph which has n vertices has chromatic number less than or equal to 5. And we'll prove this theorem for the planar graph in which the vertices are n plus 1. We have to prove that a graph G with n plus 1 vertices has chromatic number less than or equal to 5. So let G be a graph with n plus 1 vertices. So by our previous lemma, there exists a vertex V in G whose degree is less than or equal to 5. So let degree of any vertex V is less than or equal to 5. G is any graph with n plus 1 vertex. By our previous lemma, which I have just quoted, we have just proved it, that there exists in a planar graph there exists a vertex whose degree is less than or equal to 5. So we assume that there is a vertex V whose degree is less than or equal to 5. It can be equal to 5 also, or it may happen that some of the edge here is not present, so it can be less than 5 also. Okay, so we have two cases here. It is that the degree of V can be equal to 5 also, and degree of V can be less than 5 also. Now let us see what is G minus V. G minus V is a graph having n vertices. If I remove this V and all the edges here, then G minus V will be a graph which has only n vertices. So by induction hypothesis, G minus V is 5 colorable. We assume that all planar graph with n vertices have chromatic number less than or equal to 5. So G minus V will be 5 colorable. So if I remove this, I can color the graph with 5 colors like this. Okay. Now let us see if degree of G is less than 5. If degree of G is less than 5, then one of the edge here will be missing. Okay, one of the edge will not be there. So let us assume that this edge is not there. So we can use color of vertex V5 which is not connected to V. This vertex is not connected to V, so we can use blue color here. So then again G will be a 5 colorable graph. Again G will be a 5 colorable graph. So when degree of G is less than 5, then 5 colorable theorem holds. Now we have to see when degree of G is equal to 5, when all the vertices are connected to V. Then let us assume that V1 and V2 are not adjacent. Let us assume that these two vertices are not adjacent, that there is no path between V1 and V4. If there is no path between V1 and V4, then we can use same color. Okay, if there is no path here, we can use same color of V1 and V4. V1 and V4 can have same color, either yellow or green. And if I use same color on V1 and V4, then I can use either yellow or green color on V, right? So the graph can look like this, right? I'll use V1 and V because they are not adjacent, so we can use same color on both, and yellow color can be used here. So again the graph is 5 colorable. This happens when V1 and V4 are not adjacent. But if they are adjacent, if degree of G is 5 and V1 and V4 are adjacent, that is there exists some path from V1 to V4 like this, then what we'll do? Okay, then they can't have the same color, right? And then the fifth color can't be used here. So in that case, what we'll do, we'll take the another two pair of vertices. We can take V5 and V3. Okay, let's suppose that V5 and V3 are not adjacent. If V5 and V3 are not adjacent, then same color can be given to V3 and V5, and color of V3 or V5 can be used in V. So if I give the same color to V3 and V5, like suppose if I give blue color here and blue color here also, then red color can be used here. Okay, so the graph will look something like this. Same color is given here and red color is used here. So again G is 5 colorable. But if V3 and V5 are not adjacent, here we were supposing that V3 and V5 are not adjacent. But if they are adjacent, that is if there exists a path from V3 to V5, then what will happen? Then there is an edge between V3 and V5, right? There will be edge like this, but this edge cuts the previous edge between V1 and V4. So this is contradiction to planar graph. Planar graph don't have the edges which cut each other, right? So this is contradiction. So there can't be a path from V3 to V5. So this is contradiction. So G is 5 colorable. This proves our 5 color theorem. I hope you like this video and you have understood everything. If you have any query, you can ask me. Thanks for watching this video. Have a good day. Thank you.